today I'm giving some information about the exchange material and its simulation in ANSYS Fluent, how the melting behavior will change as per the time and how the melt fraction will affect with the time we are going to discuss here. And with the simulation, I'm trying to validate our results, melt fraction results, with the existing literature published in 2013, experimental and numerical study of annular PCM storage in the presence of natural convection by Lagian et al. Here they use the phase change material and try to simulate the model, which is like this. You can see the arrangement experimental setup that they have made, and they use the different location to find out the exact temperature variation during the process, during the experiment. So we can see this is the results they have achieved. So similar type of results we are going to achieve with the help of ANSYS Fluent. Already the authors done the numerical analysis with the ANSYS Fluent. So we are reflecting the same so that you will get some more idea about your future work. You can add some different arrangement of like a fin you can add, or different type of PCM material you can use for the analysis. So our aim is to validate our numerical results with the experimental outcomes from the paper. So first of all, we will see how the model is developed, how the domain is developed in the ANSYS Fluent. So initially we will start with the geometry creation. So I use the same dimensions what the authors Dengian et al. Used for their experimentation. So they have mentioned clearly about the dimensions. So inner diameter of 44 mm is made up of plexiglass that we call as a shell, and inner pipe. So inner pipe is made up of steel, which is having the thickness of 2.5 mm and having the diameter of 15 mm, and a total length of the system is 400 mm. So we will use the same dimensions for the geometry creation. This is the location they have kept sensors for the temperature measurement. So we will discuss it later. Authors suggested to use the single symmetric arrangement so that we can reduce our simulation time. So we are not creating the complete 3D model. With 2D, we are going to analyze it. Because then the number of elements will increase. It will take the time for simulation. This is the complete view of the schematic diagram. Initially, I have created the rectangle of dimensions 400 mm length, and the diameter of the shell was 44 mm. That we can see the diameter of the shell was 44 mm. But we use the symmetric arrangement to make it more simple for the simulation so that we can reduce the number of elements and ultimately it will affect the simulation time. Initially, we created the domain which is reflecting the half part of the cylinder, that shell. Best approach is use the radius, like it is 22. So you can see here 22, and this is of 400 length. Then I will go with the sketch 2 here. This is the pipe. Here the heat transfer fluid is flowing from the top of 2.7. You can see it is 2.7. Sure. So 2.5 is the thickness of the pipe we have seen in the paper, and it is having the same length what the shell is having. So 75 mm is the distance. Means the radius of the pipe is 7.5. So actual diameter is 15 mm. So we are creating a half section. So it is 7.5 mm radius. So this is the two sketches we are having. So after the sketch, to create the surface from the sketch, so simply just go here and select surface from the sketch. Then you will get this type of surface sketch 1. So once you click on that particular part, so okay, just I'm deleting this part. Okay, it is in relation with the Boron operation, so it will not be deleted. Sketch we are selecting, and then if we are going there, concept and surface from the sketch, and just after that, just select the sketch of where which you want to develop the surfaces, and select the generate. So automatically you will get the surface like this one. There are the two surfaces which I am having. So now I want to make it in 3 sections. Like we are having one fluid section, and one is our pipe, and third is our PCM storage, that is shell arrangement. We are having 2 parts here, one is fluid and another is still. So but it is overlapping, interlinking. We want 3 separate sections, like one is fluid, one is pipe, and another is PCM. We have to do, we just go the create option and select below. Now here you can see there is option unite. So unite means it will merge. It is a single part, but we don't want a single part, we want 3 sections. So what we will do, we'll make it subtract, like edit, go to subtract section and apply here extract. Then which, so this is our shell is our target bodies, and this tool body is our pipe. So we want to preserve it, still pipe and fluid. So we can rename it as a PCM, So I hope you got the idea how to create the geometry in the ANSYS workbench with the help of Boolean operation. Now let's go for the next creation. So I think it is only for two surfaces. So we should go with the three surface because it is symmetric and it is having a rectangular shape for all the fluid domain, PCM domain and pipe domain. So use face sizing, and I have given 0.6 mm element size for the meshing, and I use face meshing to get the uniform mesh. So you can see we have here some wood fine mesh. It is enough for analysis. Not worry about board quality or because the simulation our machine is somewhat okay. Fine, we can go ahead with the same machine. So update it. Now, as per there, we are given the name selection entry at the top. So our heat transfer fluid is entering at the top. So we are given water inlet. Water outlet is the bottom of the pipe here, bottom of the fluid domain. Fluid, we have given the body surface nearly here or this one. Pipe, this is the pipe, and this is PCM. So we have to go select the surface. Like if you want to give the naming to anything, a simple click. Like if you want to give the name to the edge, select the edge and click right click and create the name selection. Like that, we can give the naming. Similarly, if you want to give the surface name, then select the surface and then select particular surface to whom you want to give the name. So here, just go to create name selection and click, give the naming whatever you want. I hope you understand till that. So I have considered this antimatic. This is the symmetric view which we have seen here. So the symmetric part is on the left side. So let's go ahead. Numerically, the author says they have not given any constraint. Like they have considered the adiabatic and the outer surface of the shell. But when I tried with the same situation, adiabatic condition, the results are not matching exactly with the exact results. So definitely during the experiment, there is a heat transfer from the shell to the outer air and ambient air. So definitely we should consider the heat transfer coefficient at the outer surface of the shell, the symmetry. Then I am updating the part. So let's go with the setup. In the general, just select the transient condition and select the gravity because gravity will play an important role during the melting. So I have used minus 9.8 watt as usual. Then select the transient, keep as it is pressure reduced somewhere. So you can check the things which we have given initially by clicking on the display. For interior pipe, you can see here, this is the interior of the pipe. Symmetric line which we have given to the left part on the axis. So this is the pipe wall. This is the inlet. So the inlet you can see here and the inlet. And this is the outlet. So it is fine. Now let's move the equations. And we have the energy equation. Click it on, and it is the phase change material we have used. So yes, click on the solidification melting. So we will get this window and keep as it is. No need to change anything. Now in the material section, what the authors use. So only the authors given the properties of the PCM what they have used for the simulation. So same properties are entered here. You can see. Okay, and for the water fluid, it is already available in the database. So I just select here and click on water fluid. Okay, then they use that lexical detail from the online is still pipe available in the database. Right here, still pipe. Okay, property of the lexical was I have entered. Or you can also use the same detail of the material what I have used. Now I must move to cell temperature. Here, as we know, the fluid or fluid domain is water inlet. So heat transfer fluid is water. So we use fluid as water. In the PCM, once we add the material here in the material section, automatically you will get the option in this list. Okay, so no need to worry. So pipe is made up of steel, so it's like that. Boundary condition, let's move to the boundary condition. So it elevated, it was there. So symmetric condition, you know that symmetric was left side, and main important things are water inlet and water outlet. Okay, so water inlet, we are giving the boundary condition to the inlet, like the authors use 0.01 meter per second velocity of the heat transfer fluid. The same we have used here, and inlet condition is 325 Kelvin, the temperature, initial temperature of the heat transfer fluid. Okay, and then we use the pressure outlet, and we kept the temperature to 295 Kelvin. Now, in the solution method, so we use a simple method for pressure and velocity coupling, and we keep all the things as it is except pressure. We use the special discretization like Presto for the pressure. Then go with the pressure. So in relation to I am giving here. Then monitoring. So I wanted to this must be test here. Your window. So I use the average temperature of the interior PCM. So by inherited method. So just simply go there in the monitor section. In the surface monitor, just create. Already we have created. So just to double click on here, average, select average, select temperature, and then select PCM. Okay. So just click on the plot. Okay. Say okay. Okay, this part is done. Now go to the solution initialization. So initially we are assuming the temperature. One more thing we are having. Boundary condition we forget to view at the ability. So and I have given 3 watt per meter square Kelvin heat transfer coefficient for the outer surface on the shell, which is made up of glassy glass. Okay. So now then I go for the initialization. Here you can see hybrid initialization is done. Now important thing is here patching. So patch means what exactly we have given the initial condition of the PCM during the charging. During the charging means during the melting of the PCM. So we have given the inlet temperature of the fluid 325 Kelvin. Now we are giving the patch in its initial temperature of 295, means it is indicating the PCM is initially at the temperature of 295 Kelvin. Okay. Now activities means if we want to save our simulation, it is very useful in the post-processing, the second view of the melting, melt fraction, temperature and out. So it's better to save. Okay. Okay. So already we have done the initialization. So we done with the patching. Now go for the simulation. So as per the paper, use the time step size of 0.5 and number of time step 15,000. So that overall if we say it is 7,500 seconds. So we are hoping that in 7,500 seconds, our process will be completing simulation part. So I'm keeping all the things max iteration, time step and all as it is. So you can see the scale is good. And this is our temperature, average temperature which we have. So initial indication is whether our simulation is right or wrong. You can simply see the scale residual, how it is converging, whether it is converging or not. That one thing we can observe. But it is, in the transient general, it is difficult to predict initially. Open one window where we are giving the temperature variation with the time step. So you can see here. So initial indication whether our simulation starts fine or not. So we have given initial temperature of 295 to the PCM. So 295 it is showing. So starting point is 295. So our simulation is fine. Post processing, we have seen the autosave section. The autosave, the data which we have saved in the system, it was stored in a particular location. So it is there. Okay. This is the file. This is the file. This is the file which we have. So from there we can load the result. This is the first result. At 2000 seconds, we achieve the counters of temperature, and you can change the contours. Like here, I have given the temperature counters. So how to give the count? How to find the counters? So simply click here, counters. Okay. So this I am hiding other things so that you will get more clear view. So now this is the domain which we are having. So counters, select the counters, and here also we can change the background. Go to the blue option. Just set. Okay. So just go with the wireframe. See, you can see the wireframe. So initially we have seen how to view the counters. So here it is the domain, all domain we want to see. At every what we want to see the PCM. Okay. And apply. This is the pressure. Now you can see here the mass fraction. Here like that. So similarly, I have created the counters for the temperature and recognition. This is the counters for mass fraction. You can see this is the counters for mass. This is the counters for mass fraction also. This is the mass fraction for mass fraction. It is. So we just already know the fluid which is flowing. It is in the liquid form. So red color is showing it is completely liquid region, and the blue region is indicating in solid section. So see, in the counters we are using the temperature. So it is showing the temperature on the spot. Now, how I achieve this part? Simply just what I have done. I created the counters for the mass fraction. Okay, you can see here PCM location, and then what I have done, I created another counter, but this time I use the reflection along the YZ axis at x equals to 0. So with this arrangement, I get the mirror image of the actual results which we have at the counter 1. This is the method. Similarly, which you can see here, this is the contour for the mass fraction. That is simply one. It is a fluid. So fluid means it transfers fluid water. So to make the mirror image of this fluid counter 3, I use counter 4, and I use the same arrangement which I have given here. So apply reflection or mirroring method YZ and with respect to x axis. So I got this all the 4 counters like this. So if we want to see the temperature, instead of in the right side I am showing the mass fraction, and if I want to show the temperature variation in the left side, just simply click on the counter 2, and instead of mass fraction just go with the temperature. Okay, you can see. Similarly, for the counter 4, just instead of it is already that like that. So you can simultaneously you can show the temperature counter as well as mass counter in the same image. So if you want to save the image, you can click here, and where you want to save the image and save here. This is for 200 seconds. Similarly, you can show it for the 4000 seconds. So similar method, just go there, load the results, and from where we have saved the simulation results, from there you can upload the results for the particular time. Now this is for 2000 seconds, and this is for 4000 seconds, and this is the complete time. So this time, after this time, you can see the temperature is moving beyond the melting point temperature, and the temperature PCM in the shell is completely melted. That's why the counter 1 and 2 are in the red condition. Here the red is indicating 1, mass fraction 1. It means the PCM is completely melted. Okay. Now if we want to get the graph with the time, so here already I have, just simply click here. You can see the chart. You will get the option like this. Okay, already I have it. So just double clicking on them, and before that, now we want to see the temperature variation or mass fraction variation within the PCM. So to get that one, what we have to do, just go here the expression and create new. Now do the naming like mass fraction we want to see in the PCM. So simply mass fraction, already it is there, mass fraction. Just for your understanding, I am giving image. So here create the function like it is area image I am using, and what you want to find, what you want to see in the graph. So I I want to see the mass fraction relation at the time, so I have selected the mass fraction here. And at the location, at what location means I want to see within the PCM. So PCM I have selected and simply click the apply button. So this is the thing which I have already created. Okay, so available mass fraction, this is the thing which we have already. So similarly, I have created the expression for temperature. So you can say area of average, temperature, and at the location of PCM, within the PCM of thermal system. Now we just go with the chart. Now here you can see already we have saved the details before during the simulation. Now we want to see in the transient way in the graph, in the XY graph. So this is the XY transient or sequence. Just click on that. And after clicking on that, it will be activated. The expression command will be activated. Just go there and click. Now what we have seen here, it is temperature now. Just okay. So temperature, click on the temperature. And y-axis it will be like, x-axis is the time and y will be the temperature. So apply. So you can see chart. So this is the temperature variation along the with the tight temperature variation. So I was melting observation started at 295 and still continuous up to 324. Similarly, mass fraction